So this chapter 9 is on gas power cycles or gas power systems. It's the longest chapter in the book, and so let's just jump into it. But I'm not even going to try and summarize where we're going to go. Let's just say for right now we're going to study internal combustion engines. So if you pop the hood of the automobile that you may own or drive around in, or you will see something like this. This is one of the top 10 inventions or innovations that really have set the tone for modern civilized society. The internal combustion engine. It ranks up there with septic systems and some other things, like integrated circuits or electronics or something. But the internal combustion engine is a big deal. It's a big deal in your life, and it will continue to be a big deal for a while. So we are going to study the Otto cycle, and it's basically the Otto cycle is mimicking what happens in a gasoline. In a class like this, you should know what are the basic mechanics and mechanisms that make a V6, V8 engine work, inline, four-cylinder, and there's some great animations out there. So if you're unfamiliar with it, please look. Well, let's talk about the four-stroke cycle. So this one, I'll put it in the context of gasoline with the spark ignition, but it's true also for the diesel. And then we're going to talk about the Otto cycle. So basically you have a cylinder, and we like to show it with the hemispherical head. It could be a flat head. When you take that lawnmower apart, there's nothing sophisticated about a lawnmower. It's like the old Ford flatheads. It's just flat. The combustion chamber's like a pancake. All right. But most automobiles that I know of, I don't know of any modern automobiles that don't have that. They have a hemispherical head. And in that head, they'll have valves that can push and open, poppet valves like that. And you'll have a piston. And the piston, when it's at the top, it's what they call a top dead center. And what we'll do is we'll have 4 strokes, and each stroke moves the piston from one location to the other location, from the extreme top dead to the bottom dead center. So when the piston moves from top dead to bottom dead, right, it's drawing down, and the valve right here would be open, an intake valve would be open, and you would bring in a fresh charge of air-fuel mixture. Now, at the bottom, you're going to turn around and take the piston back to the top. With the intake valve now closed, you're going to have an exhaust valve. It's been closed the whole time so far. There's no way gases can escape. So what are you going to do to the gas that's trapped in the piston cylinder? You're going to compress it. So this first stroke is called an intake stroke because you're intaking gases, air-fuel mixture. This is called a compression stroke from the bottom dead back up to the top dead. Now at the top dead, you're about ready to come down with the power stroke. So to go from top dead to bottom dead, but the power stroke is where the gases have high pressure and they're pushing down on the face of that piston, and it's doing a lot of work, pushing down, expanding. Well, what happened right around here was you had a spark and you had combustion. So when it reached top dead, there was an explosion, combustion, very rapid combustion inside that cylinder, and it transformed the gases from the air-fuel mixture into combustion products at very high temperature, very high pressure. Now you have the power stroke. Then at the bottom of the power stroke, one of the valves will cock open. It'll be the exhaust. And when it exhausts, when it kicks open right there, the gases are still at significant pressure, such that you get Mach 1, you get sonic speed going around that exhaust valve. It'll have a very rapid reduction in pressure, but the piston, or the combustion chamber and the whole displacement volume will still be filled with products of combustion. You want to get as much out of there as possible, so the piston will move to top dead center, and as it's doing it, it'll exhaust, pushing out products of combustion. So this is the last stroke, exhaust. So at the top, after the exhaust stroke, the exhaust valve closes, and which valve opens? Intake, and you start the process. You start the cycle again. Okay, so we have the strokes: intake, compression, power, exhaust. If you're new to it, just memorize them. Memorize what's going on. In the intake stroke, where does the piston go? From top to bottom. And then what in the compression? Bottom to top, etc. When is the intake valve open? During the intake stroke. When is the exhaust valve open? During the exhaust stroke. Right. So that's the 4 strokes, and the spark is right here. And what we'll do is you model it as happening at the top, and it's all very rapid for combustion. But in reality, it takes a while. And if anybody's ever timed or watched the spark advance on an engine, engines are adjusting that all the time. They may move from a few degrees to many degrees before top dead center, where the spark plug actually goes. All right. Well, once you have the location of the piston going from top to bottom to top to bottom to top again, and you know the strokes, during this is the intake stroke, then you have the compression stroke, then the power stroke, then the exhaust stroke, and you have a good idea of when the valves are open. Oh, it opens, it closes, it opens and closes. Then we can draw out a good PV diagram. Now, on this PV diagram, we want to put in a pressure that's atmospheric pressure. That's atmospheric pressure. Okay, now, you're going to start it when you're at top dead center, and it'll have the smallest volume. So this will be the volume at state 1. We can call this state 1, or just put it at, forget about numbering them. This will be the volume at top dead center. Okay? And it's roughly going to be around atmospheric pressure. And as the piston goes down, what will happen to the pressure inside the cylinder? If you have atmospheric pressure outside, the air has to come and be pushed across the air filter, through the little ducting, through some throttle body, through some intake manifold, and across the valve, and finally into the cylinder. So where's the lowest pressure in that whole sequence? In the cylinder. So the cylinder has to be at a state of vacuum. It has to be in a state of vacuum during that intake stroke. So it comes down rapidly and you have a state of vacuum. Oh, it's not that hard of a vacuum, but it's what's drawing it across all those things that I mentioned in the filter, etc. So it's a state of vacuum. Now, when you get out to the bottom dead center location, then the intake valve is no longer needs to be open. It's going to close, and then you're going to start to compress it. And as you start to compress it, what's going to happen to the pressure? It's going to go up dramatically, isn't it? So it's going to go up, 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 up. And then maybe before you get to top dead center, the spark fires, the spark plug fires. Now you have combustion. You've been compressing it. The pressure's been going up as well as the temperature's going up. Now what's really going to go up? The pressure and the temperature are really going to go up now. So it really takes a dramatic increase in pressure. And then you begin what other stroke? So this one was the intake stroke. This one was the compression stroke. And we're about ready to begin the power stroke. And as you begin the power stroke, the pressure will come down as you're expanding the gases, or the gases are expanding. You're not really. I mean, it's happening. And it comes down here. And when it comes down here, what happens right around there? Exhaust valve opens. There's still a significant pressure in that cylinder. You will get a loud pop. If you don't believe me, take the muffler off your car and drive it around. Some people do in my neighborhood. I can hear them for 2 miles away. Do you know what I'm talking about? It's loud, right? But that's why you have it. And so the muffler. Then there'll be a rapid decrease in the pressure, but I'm still going to have to push out the remaining exhaust products as I go through the last exhaust stroke. So that's going to be slightly above atmospheric pressure during the exhaust stroke. This was the power stroke. Why does it have to be slightly above atmospheric pressure, the exhaust stroke? Because it has to push it across that exhaust valve, through the exhaust manifold, through the catalytic converter, through the muffler, through the tailpipe, and finally dump it to the atmospheric outside. So this is what it really looks like. Does it stay constant? No. As you load the engine, guess what opens up? And as you idle, guess what collapses down? Because isn't this a visual indication of the work per stroke? Yeah, it's the same concept. So we want to analyze that system, and we have to introduce a simplification so that we can do the analysis. And so we introduced basically an air standard analysis. So what do you focus on? A fixed amount of air, which is always trapped in the piston cylinder apparatus. You're saying, isn't there fresh air, fuel coming in, and the exhaust products going out? Absolutely. But to make this analysis doable, what we do is focus on a fixed amount of air only that's trapped in the piston cylinder. It always stays air. There's never a transformation to the carbon dioxide, water vapor with a lot of nitrogen in the products of combustion. It always behaves as an ideal gas. So we know that when we say it's an ideal gas, 3 things: PV is equal to RT, internal energy is a function of temperature only, and enthalpy is a function of temperature only. And the combustion process is too complicated at this point, so we just replace it conceptually with a heat transfer at constant volume. So if you're just going to have a heat transfer coming in from an external source happening at a constant volume when the piston's at, I forgot, what is TDC? Top dead center, that's right. There's no exhaust or intake. You just simplify that with a heat transfer. Where? At bottom dead center. And all of the processes are going to be internally reversible. At this point, we can resketch the pressure volume diagram. So we're just going to think about starting with compression stroke. The compression stroke down to top dead center. Heat addition at constant volume will bring that pressure way up. Then we're going to expand power stroke, and then heat rejection at constant volume finishes off our cycle. So we have 1, 2, 3, 4 states. We have process 1 to 2, then 2 to 3, 3 to 4, and 4 to 1. Again, what is the states are numbered 1, 2, 3, 4. And then you have the process from 1 to 2. What's happening in this process from 1 to 2? Compression. What's happening 2 to 3? Heat addition. Heat in. Q in. 3 to 4? Expansion. And 4 to 1? Q out. Are all of these internally reversible? Yes, they are all internally reversible. When you have the compression, do you think there's any heat transfer from 1 to 2 during the process 1 to 2? No. How about from 3 to 4? No. You just have the heat transfer in and out. That's it. How about the boundary work? How much is the work 1 to 2? Is that a large positive, large negative, or 0? It'll be negative because you're putting work into the gas by compressing it. How about the work 2 to 3? 0. That'll throw a lot of students for a loop. See, a lot of you know that right now, but I bet there's a few out there that are saying, what? Why is the work 2 to 3 equal to 0? Because I'm not expanding or compressing. The only way we have boundary work is the integral P dV, and if dV is 0, I don't care what P is doing. P is going up, but there's no dV. All right, what about the work 3 to 4? Large positive. And then the work 4 to 1? 0 again. Now, we can make the analysis even simpler. It's the air standard analysis. If you see the word in front of it says cold, if it says it's a cold air standard analysis, then it's even simpler, because what you assume is that the specific heats, you model changes in internal energy, changes in enthalpy as using specific heats evaluated at the ambient temperature, either 298 Kelvin or 300 Kelvin. There's so little difference, I don't make a distinction between the two. Typically, it's 25 degrees C is the temperature for which you evaluate properties at cold air. And again, why are we doing all this? So we can make a simple assumptions, to make a simple calculation, and then evaluate the performance. So here is our pressure volume diagram. I know I just sketched it for the Otto cycle. Here is our other favorite diagram, a temperature entropy diagram for the Otto cycle. And what I'd like you to do is I'd like you to sketch all of these on the PV. Hey, if you were taking notes, you got it. And also on a TS. For what? For the process that goes from 1 to 2, 2 to 3, 3 to 4, 4 to 1. And what will be the process from 1 to 2? Let's start that one by saying it's compression and it's adiabatic compression. Okay? So that helps you place where state 1 is. Can you do that? Did everybody get it? So we just did the PV, right? You put state 1, you compress, state 2, you go up to state 3, down to state 4, then heat rejection. Sometimes they'll put like this. What's that indicate? It's adiabatic. Adiabatic power stroke as well as adiabatic compression. Sometimes they'll put this will be like Q in, and then this will be Q out. But we know that by our sign convention, Q out is negative. Okay. What about on a temperature entropy diagram? If you have adiabatic and it's internally reversible compression, is that S equal to constant during the compression? Isentropic? Isentropic. So we would start here, it would go 1 to 2, and it would be a straight line up on a TS diagram. And then from 2 to 3, the temperature is going to go up. While we add heat, if we're adding heat, entropy is going up. We're adding entropy. Then from 3 to 4, we have isentropic power stroke, and then your heat rejection. So that's what it looks like on a TS diagram. So hopefully you have all of these: constant volume heat addition, adiabatic expansion, constant volume heat rejection. Then once we have a good idea of these diagrams, then go for writing the first law for each of these processes. So what does the first law look like for process 1 to 2? I'm going to pause, walk around. All right, so the first law, this should not be hard. This should be really easy. So we should write almost from memory something like, well, the final internal energy minus initial internal energy, some people are writing the change in internal energy, that's the same, is equal to how much heat is transferred in from the process, during the process from 1 to 2. So we add that subscript because we're going to write it 4 times. Minus the work, boundary work, positive out, during the process 1 to 2. Do you like this as a first law? Did you have something similar? Yes. If you had an M dot in there, what do you think? Wrong. If you had an H in there? Wrong. Oh, you've got to be really careful. And I would, because we know that we're going to do it for the process 1 to 2, then we're going to do it for the process 2 to 3. Let's write it for the process 2 to 3. U3 minus U2 is equal to Q. 2, 3 minus work, 2 to 3. So let's keep the subscripts clear so that we know okay, this work is different than this work because of the different process. All right, let's do it for the process 3 to 4. U4 minus U3 equal to Q, 3 to 4 minus work, 3 to 4. And then 4 to 1, U1 minus U4 equal to Q, 4 to 1 minus work, 4 to 1. Now, I know some of you already started rearranging, but let's strike out the terms that are 0. Some of the Q's are 0 because it was adiabatic, right? So if the process is adiabatic, which of the 2 of the 4 Q's are 0? Q1 to 2 is 0, and 3 to 4 is 0. And we already talked about 2 of the 4 works. Work, 2 to 3 is 0, and 4 to 1 is 0. That's right. So at this point, it's really, some people did this. They said, oh, I know what work 1 to 2 is. They said from here, they're able to say work 1 to 2 is equal to U1 minus U2. But make sure that we don't introduce a negative sign error. We have to do that correctly. Okay. Somebody says you're doing a cold air standard analysis. I can replace the delta U by CV T1 minus T2. Now I have it in terms of temperatures. Make sense? All right. How about now for the Q? Maybe I didn't leave enough room here, but this let me just draw it over here. Sorry. Q2 to 3 is equal to U3 minus U2 is equal to C sub V T3 minus T2. And this work, 3 to 4, is equal to U3 minus U4 equal to C sub V T3 minus T4. All right, I'm really going to focus on this equation right here and this equation right here because I get a lot of questions about that. I get a lot of questions. You know, I put up my things in YouTube, and yes, I do have errors, and that's nice. People find my errors and comment. That's good. But sometimes people correct me when they just don't know what they're talking about. This is one of those times. All right. During the process from 1 to 2, is it a constant volume process? What's that V on that C indicate? Constant volume. Hold it. You're using a specific heat, C sub V, that says it's for constant volume, and you're using it to calculate the work. 1 to 2 is C sub V, T1 minus T2. And this is not a constant volume work. It can't be a C sub V. Why? Because in the ideal gas assumption, U is a function of T only, and U is the rate of change. C sub V is the rate of change of U with respect to temperature holding V constant. But if U is a function of T only, this turns from a partial derivative to an ordinary derivative. And it's straightforward. du is C sub V dt, regardless if it was constant volume or not constant volume. If it's an ideal gas, that's true. All right, so the same thing is down here. And then the last one, Q, 4 to 1, is equal to U1 minus U4. And if you use constant specific heats, that's C sub V T1 minus T4. With that, I'm going to go ahead and stop. We'll pick up there next time.